Yes, we can say it. Thank you.
Thank you. Then I will start. I hope you can hear me loud and clear. If not so, please tell me. I'm here today to present agent. I want to present the work of our research group that we did on agent-based modeling of Ethereum consensus. I will go through a short introduction, introduce the motivation behind the model. Then I will talk briefly about consensus. I will talk briefly about the concepts in Ethereum proof of stake that we try to model and that we try to replicate in our agent-based model. Finally, I will explain how the agent-based modeling approach we are applying works, and then I will present brief results that we get from applying this model and using the simulations. And finally, I will conclude it. So first I wanted to introduce the paper and myself. I'm Benjamin Kraner. I'm a PhD student in my second year at Professor Tessone's group. We're doing research on blockchain and distributed ledger technologies. And I'm originally an economist, so I will not bother you today with code, but I will try to give you a little bit different look at how to study consensus and blockchain systems. I want to also thank my co-authors, Nicolo Vallarano, who's a postdoc in our team, and Claudio Tessone, who's the professor here, and also Kaspar Schwarz-Schilling, who supported us from Ethereum Foundation and who's a colleague of mine. So yeah, let's start with the introduction. So some months ago, I stumbled upon this image, which is a clock in Paris in the late 19th century. And basically, at some point during the history, railways came up and people suddenly had the urge to synchronize clocks across the city. Because for the railway services, it was a huge problem to have desynchronized clocks. Since if a train runs at 1 o'clock in the afternoon and arrives at the place a half an hour later, people have to know what time it is. So Paris built a very interesting system where clocks were controlled by a pneumatic system. So compressed air was put through some pipes, and then the clocks were synchronized. This was a centralized thing. Okay, so there was a central air compressor, and they basically did this for, let's say, 20 years. At some point then, what happened was that a flood came to Paris. So the Seine overflew and the compressor station was destroyed, and they switched then to electrical clocks. Why is this important? I think it's an interesting story because consensus at some point in information systems becomes very important, and so it is in today's blockchain systems. What makes these systems more complicated, I think, is the distributed, decentralized nature of them. Here we had a centralized system, and it had an obvious weak point, and it failed at this point. And we want to make systems nowadays, especially computer systems, more resilient to such failures. Hence, I think we went into decentralization and distributed computing. So our main motivation for this agent-based model is under what circumstances will consensus be achieved in blockchain systems. We're studying Ethereum, and we want to model basically the peer-to-peer layer of information exchange in Ethereum to understand under what parameters can we observe consensus, especially with the focus on latency, and what implications the network structure of this peer-to-peer network has for consensus. Finally, we want to test different parameter settings to understand, hey, in this region, we have efficient consensus. There are no nodes that cannot communicate with the network or that produce blocks in vain. So that's kind of the research topic we want to focus on. Now, what is consensus? Consensus it refers to a state in which all the peers in the blockchain network understand what is the correct and current state of the data in the network. So everybody has the same view, in our case, of the blockchain. it is really important that consensus is achieved, because if there is no consensus, what will happen is that some nodes will fork away, so they will produce blocks at the same height, and this will basically mess up the view of the blockchain that this whole system has. So one part could have another transaction history than the other part. And if that would happen, right, if you would have a fork, this would be very costly, because then you would have to you would have to redo the transactions, and yeah, you would have to settle which fork would be the correct one, etc., etc. So this is very bad for Ethereum and for any blockchain system if their consensus wouldn't be given. So consensus is important. Why is it so hard to achieve? Because I think centralized systems here have a much easier. Centralized systems don't necessarily require consensus. You have banks, you have governments, everything that maintains central databases, and they work very efficiently, and don't need these consensus protocols that blockchain systems need. That is because they are centralized, right? Because blockchain systems are decentralized. We need to have stable consensus protocols that allow us to maintain this state of the data across all peers. So just as an example, if you take a look at the left network, it's a star graph. You have this orange node which controls everything. On the right side, you don't have this thing where peers are connected more independently among each other. So here I have I hope it works, and you can see it in the presentation. I have a GIF of a peer-to-peer network in which blocks are produced. And basically what you can see here, the nodes follow a very simple consensus mechanism, which would be the longest chain rule, okay? The consensus mechanism in general in proof of stake or proof of work in Ethereum and Bitcoin would entail more things, but here, just for a depiction of it, it's simply the longest chain rule. And what you can observe here now at the system, at some point, one node produced the block or added some information to the blockchain. In this case, the orange block that was added, and then the blue node created another piece of information, attached it, but the spread throughout the network is different. So here in this case, this gets solved by simply accepting the longest block, and then we enter again into a state of consensus in the end. And what is interesting here, I think, what I'm trying to show here is basically that you can have these kind of forks even without like any malicious actors in the systems, but simply because of latency that you have in information transmission, forks might occur. So somebody is not informed that somebody else added something to the blockchain, to this ledger, and then he creates a piece of information, wants to attach it, and you have this kind of fork. So basically, the key point here is that the consensus mechanism is needed if we want to ensure that peers are synchronized despite of latency. Let me come to proof of stake Ethereum. So Ethereum, yeah, I guess everybody knows what Ethereum is. One of the first and biggest blockchains. It used to work on proof of work, so like Bitcoin. In September 2022, the merge happened and it migrated from proof of work to proof of stake. It introduced a separate blockchain layer, the beacon chain layer, which differently, the consensus layer, which is run on the beacon chain, which is handling the whole proof of stake mechanism in Ethereum. So basically, miners have been replaced by validators, and a slightly more, compared to proof of work, in my opinion, more complicated system. I want to focus. I don't have the time and neither the knowledge to explain the whole proof of stake system in Ethereum, but I want to focus on certain aspects that we try to embed into the model and represent there. So what we will focus on will be the temporal aspects that we have in proof of stake Ethereum. Then I want to quickly explain what the validators are and basically how the fork choice rule works inside the validators. So in a grand scheme, Ethereum proof of stake has two timescales. One would be the epochs and one would be the slots. So a slots is a 12-second it's basically a 12-second window interval where, most importantly, for our model, two things will happen. So somebody will produce a block and people will attest. How this works is you have a committee of 1/32 of the total number of validators, which get packed into a committee for a specific slot, and then they will vote and say, hey, yes, we like this block, or no, we don't like this block, or we like the block from the previous slot. So the slots are there to basically manage when block creation is happening and when attestation is happening, so voting inside of Ethereum. The epochs, on the other hand, control who is going to propose blocks when. So they are assigning to each slot a proposer, a validator that will create the block and append information to the blockchain. And on the other hand, also the committees are created in the beginning of an epoch. So you will have an assignment of these validators go into these slots, and they will have to vote on these blocks. There are other things happening in epochs, like also rewards are being paid out on an epoch level, and milestones are, I think, created inside of it. But these are more technical and are not that important for our agent-based model at this point. So let's come to the validators. Basically, validators require stake. So how it works in Ethereum, you have a contract, a smart contract, in which you deposit some stake. So I show that I have the funds and I'm ready to risk them in order to take part in the consensus mechanism of the blockchain. So I'm basically telling the system, hey, I have 32 Ether, I'm going to stake them. And if I make a mistake, or if you find me acting maliciously, I will be punished, and I accept this. So I cannot just simply remove the tokens, but I have to keep them there for some time. And that's what basically a validator does. He provides stake to the system. That's why, hence it's called proof of stake, right? One person can activate a multitude of validators, basically to add more stake, to represent how much stake he has in the system. But that is on a technical level, I think, enough for a modeling of it in an agent-based model. Finally, exactly, the validators are the entities that create new blocks, and they vote on the state of the blockchain, so they attest. This whole process is incentivized within the system by paying out Ethereum-denominated rewards to the validators that behave correctly, right? And on the other hand, if you have bad actors that enter the system and want to rip it off, say they produce blocks that don't comfort with the protocol, or that try to change the state of the system, basically they can be slashed. Like I said before, you will lose a part of this stake that you have. This whole stake also then secures the system, because you have a lot of investment into the consensus mechanism, which makes it to a certain extent secure, because I cannot simply enter the system and say, I buy this or I create 1 million validators, right? But I have to have the funds beforehand. So I want to, yes, exactly. Like I said, maybe the two for our model, the two most important things for a validator are that in each slot they will have the duty to propose a block. So as I said before, in each slot, one of the validators will be selected at the beginning of the epoch, and then he will have to build and propose the block. By the building, we don't really model, but we model basically the creation of the block and then how it's disseminated throughout the network. So he builds a block, and then he starts to spread it around through his network of peers. Finally, also the testing, right? As I said, they will have to vote. So every validator will basically have to vote once in an epoch, and they will have to do this. I think in Ethereum you have to do this also in other committees, not only in attestation committees, but for us it's mainly important that you have this attesting committee and that validators vote on the correct head of the blockchain. So basically they're looking at the blockchain, and I will come to it in the next slide, but they look at the blockchain and then select which one is the block they should build on further, or that they say is currently the most recent state of the data. this whole thing, right, whether they are a proposer or they're in an attestation committee, this thing happens at the start of the epoch and basically is decided by a random algorithm within Ethereum. So I want to come to the fork choice rule, and that was what I was speaking about before. They have to determine which block is the correct one. Now, in Bitcoin with proof of work, it was pretty easy because you could produce this proof of works and you look at the longest chain and you know, aha, this is the one I have to choose because there was the most work input into this chain. So it makes a lot of sense that I attach it to simply the longest chain. Here, on the other hand, I need to take into account the votes of the validators. So Ethereum is using an algorithm called latest message driven greediest heaviest observed subtree, LMD ghost in short. I don't want to go into the specifics, but basically what you do is you count the votes that you have on your block tree, and then you basically decide for the one leaf that is the heaviest to be the head of the blockchain. Let me come to the agent-based modeling part, and I hope I will find everything that I mentioned before now again here. First, I wanted to think about, I was creating this presentation and I had to think to myself, why is agent-based modeling actually a good thing in this context? And I think agent-based modeling for blockchain systems is it's a very appropriate methodology. Why? Because we are simulating computers interacting with each other. Of course, there is a human level, I can change certain parameters, but the protocol is pretty rigid. So the action space and the decision space of these computers is limited in some sense. And if you have if you're following strictly the protocol and if you assume that you don't have bad actors, I think it's actually quite a reasonable representation of this system, which can be simplified and lends itself to give us insights into the functioning of a system that we cannot observe in the real world simply like that, because it's too distributed. It's not. I cannot have a whole overview over every node in Ethereum. Here, though, I can, and I can simulate certain things. So I think it's a very appropriate methodology. I think, and I will come later to it as well. We're applying the methodology that was proposed by Professor Tessone in an earlier paper where they're creating a minimalist stochastic model of a blockchain, of Bitcoin in that case, which works very well. In my opinion, it neatly ties together the different processes and basically gives very valuable insight into how to model such protocols. So I can tell anybody that if he's interested in agent-based modeling of blockchain system, I think this is a really good starting point. What was difficult for us adapting this model was basically that in Bitcoin you only have stochastic events. So everything is happening randomly. You are creating blocks randomly because you're solving the hashing problem, the proof of work. On the other hand, in Ethereum, you have a rigid time structure. You have fixed time events, deterministic events that are happening at certain times and point. And this was basically the main issue that we had, or the main problem that we had to overcome to model this. So I want to describe what the state of the system is like. And we can do this. We have an implementation on GitHub, which I can also share with you. I didn't include the links here, but we have an implementation in Python. And I want to describe basically the four main components I see that describe the state of the system. So the first thing that you have is you have a set of n validators. You have a certain number of validators, whatever you can use, whatever number you want. And they're basically just data objects, right? That hold them different, that basically are defined through the relation to the other objects that you have in the space. Apart from the number of validators, you have the peer-to-peer topology, which then dictates who can communicate with who. So, like you see in the bottom right, small image, it depends. I can only share information with a neighbor of mine in this network. And then finally, what you have is that each of these validators has its own set of blocks and its own set of attestations. Why is this important? We want to exactly understand what is happening in those different views of the blockchain, how these different block trees are formed, and how the attestations are aggregated within a single validator. Now the question becomes, when we describe the state, okay, we have the starting state, we want to describe also how the system evolves. So what is the evolution of the system? And for this, we define events that can happen, that alter the state of the system. And here we have to make a distinction between stochastic events, which are like block gossip, and attestation gossip, which means how are the blocks and attestations being sent through the network. And on the other hand, we have to think about deterministic events that are given by the protocol of Ethereum, exactly like the things I mentioned before, hopefully. So we have the slot boundary, the epoch boundary, and an attestation boundary. I want to quickly explain how these events work. So basically, whenever a block gossip happens, we choose an edge from the network, and this defines the sender and the receiver. Then the sender simply sends its head of the blockchain to the other. At each point here, everything is evaluated always with LMD Ghost. So this is maybe important. You have this set of blocks. Validators always run LMD Ghost. They decide, okay, this is the head of the blockchain, and I want to send it from me to the other node. So in this case, the sender sends its head of the blockchain to the other node. The other node updates its system. It checks whether it is the head of the blockchain for him as well, or for it as well, with LMD Ghost. And then, if it's within, so what I did not mention, I will mention it in 1 second. And then basically it creates an attestation. There are some small differences, but it creates an attestation, if it's accepted as the head of the blockchain. Finally, the attestation gossip, it's exactly the same thing, but in this case, we just don't need to evaluate it with LMD Ghost, but basically we're just sending the information about the attestations to another node. And that's it. Then they update this set. Now to the deterministic events. We have an epoch boundary, and basically this happens every time 32 slots pass. You will have proposers. You will have a proposer selected for all the 32 slots, and you will have committees created for each of the slot. Then you will have the slot boundary, which is basically happening every 12 seconds in system time. And then basically the validator that was selected already in the epoch boundary is chosen, and he creates a new block object that is referring back to the old state of the blockchain. Then finally, the attestation boundary, I left it out before, but this basically happens at a fixed time into a slot, 4 seconds, because it is like that. So these are all parameters, so the times can be changed, but we are trying to model Ethereum, so we use we use the details or the parameters of Ethereum. So in this case, the attestation boundary happens 4 seconds into the slots, and at this point, every member of the attestation committee will will create an attestation, no matter if it received the newest block or not. The question becomes now, how do we tie everything together in this agent-based model? And the answer is that we are applying the Gillespie algorithm. So this is something coming from physics, from stochastic modeling of gases, I think. I'm not in chemistry. Sorry, not physics. Exactly, from chemistry, comment from my professor. And it basically assumes that you have independent Poisson processes, and you can take the superposition of them and then evaluate first the next time increment and then the event that you have to choose. And they're all being, you don't just randomly sample, but you sample according to the rate at which the system should occur. This should allow for a correct, basically, selection of events and incremental and inter-event times that you have in a system. So on a grand, let me quickly how this looks in the model. We sample from the common distribution of zeta here. Then we increment. We select the time increment. We increment that time. We check whether within this time an event passed that is a deterministic event. If not, then we simply execute the stochastic event. If there was a deterministic event, so a slot boundary or an epoch boundary, we execute that event first, and then we execute the random event that we selected before. Maybe here is an image of how this process looks, a bit abstracted. So basically, you have this fixed time event. Okay, now consider that this is time 0. Maybe I can do it with the mouse. It's better for the online people. So you have here time 0. We start this process. We select the time increment. We generate here. Let's say we have a block gossip. We have a block gossip. We create these time increments. And then if the time increment goes over this epoch boundary, or this attestation threshold, we basically tell all the nodes, hey, you have to create attestations now. And so on. We can do this for any time, and it's basically just like it represents then the structure of Ethereum with a lot of random events in between that symbolize the transmission of information on the peer-to-peer layer. So I want to come to the results that we have, and I want to introduce first, because how do we measure results in this? I mean, results is a pretty abstract thing. Okay, you have to first understand what you want to measure in the systems. And so we are applying two metrics. One is very simple. One is the main chain rate, which just means how many blocks can we identify at the end of the simulation in the main chain, given by LMD Ghost, or by looking at the longest chain, for instance. Here we look at the heaviest chain, and then we basically just look how many of these blocks ended up in how many blocks are in the main chain and how many blocks were produced in total. So how much output or how much waste did the whole consensus mechanism produce? So you see a nice example. In this case, you have a very high main chain rate because this white block was produced and not attached to the main chain, and then you see that you can basically go through and you get a lower and lower main chain rate. The second metric I want to present is the branching ratio, and this will simply measure how many blocks you have that are produced that will fork away from the main chain. So in this case, we would count how many 1, 2, 3, 4, right? 1, 2. So you can kind of start to think about how the block tree is structured. So you have a either if the branching ratio is very high, you will have a lot of blocks that go away, but probably the fork length will be shorter than if you would have a low branching ratio. So in the model, what are we looking at? We have two main parameters of interest, which will be the tau block and the tau attestation. The tau block will be the average waiting time between block gossip events. So what is the latency in sending blocks from one node to another? And on the other hand, we have the attestation of the tau attestation, which is referring to the average waiting time between attestation events, attestation gossip events. So how long will it take for a attestation to transverse an edge in this network? Finally, what we can also change and what we can play around in this model would be the number of agents that we have and the average degree that we have in this peer-to-peer network. For these experiments, I will show you, we used an Erdős-Rényi random graph with 128 nodes and an average degree of 8. And I think my time is almost running up. If I may take 2 more minutes, I think I will finish. We have here the first result that I want to present is basically, so on the x-axis, you can see the latency of the attestation. And within the colors embedded, there is the latency of the blocks. So what you can see is that basically the main chain rate stays the same no matter how the attestation latency evolves. It starts to slightly drop if the block latency becomes very high. But here, in my opinion, if I have to interpret this, it basically tells me that latency that attestations observe will not play a role in the formation of the blockchain. Maybe here, if the block rate is if the block transmission is very slow, you start to see something where like the branching ratio starts to increase, so you have a different structure of the block tree that you can observe due to a higher attestation latency. What's more interesting, I think, is that you see this kind of phase transition, which is very logical, because okay, so let's focus away from the attestation latency because it's not that important. We want to take a look at what happens if the latency of sending blocks throughout the network increases. And we observed that here at some point, let's say at 10 seconds, this starts to deteriorate quickly, okay? And so you witness this kind of phase transition where you go from a state in consensus to a state where consensus is not given anymore or goes almost to zero. So what we observe is that the system goes out of consensus when not all peers can get the block in time, okay, for the slot. So they are attesting or they're already creating a new block, and that's basically what we are thinking is happening. What we started to look at was basically that we thought about when does it happen that not all peers are having the same information, and we approximated this by taking the diameter of the graph that we have, and you can see the red dots in this picture are basically the diameter times the block latency in the system divided by 2. And then basically when you get over a threshold of 12 seconds, which is the slot length, you'll get to a point in which basically the transmission of information is not fast enough inside the network to ensure that everybody has the same block, okay? And then people start to fork out because they don't have the information, and we have forks and we are not in consensus. This was it for the results. The conclusion, we presented the simple agent-based model of Ethereum consensus. It enables us to study how information flows inside it and how basically consensus is formed and under which parameters consensus is formed. We see that if the block latency is very high, we are very likely to be in a non-consensus state. On the other hand, we understand that the attestation latency might be less important because blocks are being created by honest actors. That's my hypothesis here. And finally, we show that the topology of the network here influences how when the consensus deteriorates. So when basically the network becomes too large, you would have to have a lower and lower latency in the system. Finally, what we would like to do further, I think it would be good if we could improve the computational efficiency of these models and if we could study different topologies and the influence it has on consensus formation, especially if we could provide a theoretical derivation of why we have such a threshold and the phase transition at a given point. And then more general, I think it would be very interesting if we could include the whole incentive structure of Ethereum on it and study what happens in some theoretical settings. Is there a skew towards certain validators? Does the place inside the topology of the network play a role for how many rewards I get? How well I can extract Ethereum from the system? And finally, you can also study attacks on it, which goes also hand in hand, I think, with the economic incentives that you have. But you can also study attacks, like you could study eclipse attacks or balancing attacks. And you could also model within it proposals that might offer a solution to such problems. And that's it from me. I think I slightly were too long, but thank you very much for listening. Do we have time for questions, or it's the next one? I'm glad to take questions if you want.
Thank you so much, Benjamin. Any questions from here? Okay. Thank you once again.
Thank you.
Now let's move forward to our next speaker.